Okay, we are launching into Chapter 7, which is intermolecular forces. Chapter 6, which you'll watch at home, is all about orbitals. Now, I will say up front, Chapter 6 has lots of valuable information in it. But I also want to put your mind at rest. Very little of that information is going to be tested. There's a few important things that you need to take away from it. And the rest of it is really to help you to really lay the groundwork in the future. Because when you talk about bonding and orbitals in a future chemistry class, it might be with a professor who really understands it and thinks it's so simple and therefore just says it to you and thinks, oh yeah, you'll get it because of course it makes sense, when it's really complicated. So I do recommend watching those lectures. But if you look at problem set 6, it's mostly just more practice with Lewis structures. All right, so chapter 7 is now, once we make molecules, what makes molecules stick to each other? So we'll start with a quick review of our different kinds of substances. Really 4 different kinds: metallic, ionic, molecular covalent, and network covalent. So what can you tell me about metallic substances? All right, they're shiny. Why? Let's go to, instead of just properties, let's go to their structure. All right, they're malleable. No, that's fine. I'll put them down. Shiny, malleable. All right, they have an electron pool. So metal atoms. Sharing valence electrons in a common pool. So the picture in your head would be a bunch of atoms and then maybe some free electrons roaming around there. I don't know. The atoms are just kind of stacked up on top of each other. All right, ionic. What can you tell me about ionic? All right, they sometimes dissolve in water, but I'm just going for the structure. All right, they're brittle. They're brittle, etc. Not properties, but just structure. All right, electrons are localized. How? Just give me the story. All right, nonmetal steals electrons. All right, metal loses to nonmetal. They form positive and negative ions. And then those positive and negative ions, come together to form a repeating pattern in what we call a crystal lattice. So there, it's positive, negative, positive, negative. Okay, metallic, ionic. Now we get to covalent. So what's going on in covalent bonding? We have two different ways it can happen. All right. So for covalent, these are sharing pairs of electrons between individual atoms. And how are molecular and network covalent substances different? Juliet? Yeah, so for molecular, it's small groups. And I use the term small loosely. I mean, small could be 10,000 atoms, but on the order of a mole, that's still really small. So small groups of atoms make individual particles called molecules. And molecules only are only weakly attracted to each other. That's what we'll get to. But the point is they're discrete particles. Whereas network covalent would be huge numbers of atoms make a solid in which covalent bonds connect the entire thing. All right, so those are our four different kinds. Now, I drew a picture for metallic because the picture in your mind for metallic substances should always be more or less the same. For ionic, similar. I drew a picture because you should always have a similar picture in your head for ionic substances. For network covalent, well, it's a little harder to draw a picture, but essentially you have this covalent bonding going out in every direction. And if you look up a picture of diamond, you'll see network covalent solids usually have this repeating pattern as well. For molecular, we don't have a simple picture in our heads. Why not? Exactly, there are too many different kinds of molecules. Molecular substances are the most interesting because there's the widest variety. You can have small molecules like water. You can have slightly bigger molecules, slightly bigger molecules. You can end up with huge molecules. I think this here is some sort of steroid. Maybe that's cholesterol. You can have DNA. You can have this molecule here, which I think is called mitotoxin. It's either paleotoxin or mitotoxin. Some neurotoxin. It's probably found in some marine organism. The point is, there is a huge variety. Because instead of forming just this repeating pattern, you can form any number of combinations. You know, the number of molecular substances is infinite. And every one is going to have its own chemical behavior and its own physical properties. What this chapter is focused on is the physical properties. So because we have different kinds of molecules, they're going to be attracted to each other by different kinds of forces. And that's what we're about today and tomorrow, maybe the next day, however long it takes. So intermolecular forces, just breaking it down. Inter is a good prefix to know. Inter means what? Between. And yes, there was a shout out to Latin in the class. So inter means between, and then molecular means molecular, so between molecules. So when we talk about intermolecular forces, we are talking about the forces of attraction between molecules. Now, I want to say something very strongly up front. And what I want to say is, these are not bonds. So for example, on quiz 4, there was a question about CH4 and diamond, difference between a network substance and a molecular substance. And I got some responses that talked about the bonds between CH4 molecules. I want to very emphatically tell everyone to remove this from your vocabulary when you're talking about intermolecular forces. This word bond is kind of strange because a bond is just another word for a strong attraction. And we don't necessarily have an official cutoff for what strength of attraction meets the criteria for being called a bond. And you'll even see that there is one intermolecular force that we call bonding, which if I could, I would change that, but I can't. But I want us to use the term bond to mean covalent bond or ionic bonding or metallic bonding. So for us, bond should be reserved for covalent, ionic, or metallic. So I don't want to see the term, the bonds between these molecules are, no. Instead, what should you say? The attraction. Yeah. All right, so what we're going to do now is just categorize the different ways that molecules get attracted to each other. And I don't want you to think of these as completely new concepts. They are all based on electrostatic attractions. So even though we might talk about dipole forces, that's not a new fundamental force in the universe. Dipole forces are just a special case of Coulombic attraction. Coulomb's law. Opposites attract. We'll talk about dispersion forces. Those aren't a new fundamental force. They're just based on Coulombic attraction between positives and negatives. Okay? So don't think this is all new. We're just using new words to describe specific cases of opposites attract. Okay? So, first off, I'll talk about a force that's not even an intermolecular force. Why is this not an intermolecular force? Go ahead, Joel. It's lattice energy. It's between ions, and it's not between molecules. So, I will start by saying this is not technically an intermolecular force. Really, this is a type of bonding. But I put it here to contrast with the intermolecular forces. So notice I use the term bonding for this. So we'll contrast this with the intermolecular forces. And the key difference is that intermolecular forces are based on attraction between partial charges. All right, so let's look at our first intermolecular force, and that's what we call dipole-dipole forces, dipole-dipole attractions. So in a polar molecule, remember we have a positive end and a negative end. And so if I'm going to put polar molecules near each other, there's going to be some automatic attraction between them. So imagine that I have another molecule drifting nearby. And don't necessarily draw this yet. Let's say I have another polar molecule that starts to come close to this one. What's going to happen as they approach? Think about it for a moment. Talk to your neighbors. Okay, what did we decide? What would happen? All right, the negative side of one is going to attract to the positive side of the other. So as I've drawn it right now, this molecule is probably going to flip over, because right now I have the two negatives near each other. This negative is going to want to get away from that negative, or it's going to just slide over so that the negative can be near the positive. So instead, we'll end up with partial negative near partial positive near partial negative. And so there's going to be an obvious way for these to arrange themselves to minimize the distance between opposite charges. That attraction we call a dipole force or dipole-dipole force. Yep. Yeah. So the student question is, does it make a difference how partially positive and how partially negative it is? And the answer is definitely. So the greater the magnitude of the partial charges, the stronger the attraction is. So for example, if I take just for a simple case, if I have HF and I have HCl and I have HBr and I have HI, if I take those four molecules, which one's the most polar? HF is by far the most polar. Which one's the least polar? HI. So the strength of dipole forces will decrease from left to right here. So as we go from left to right in this group, as I chose them, this way we have decreasing polarity, which will correspond with decreasing dipole force strength. All right, so if I have a polar substance, there will be dipole-dipole attractions. So these are present in all polar substances. Now, what if I mix a substance that's polar with a substance that's ionic? Like if I put sodium chloride in water, there I have water, which is made of polar molecules, and I have sodium chloride, which is made of ions. So there we're going to get what we call ion-dipole interactions. So this is the attraction between an ion and the partially charged ends of polar molecules. So if I have a sodium ion and I put some dipoles near it, how are the dipoles going to arrange themselves around sodium? So here I'll just draw my, I'm going to just draw my molecules like this, like blobs. But where would I put the partial positives? Where do I put the partial negatives? Partial negatives would point towards the middle. Partial positives towards the outside. And just for fun, let's do a, if I had a chloride ion. If I had a chloride ion, I'd see exactly the reverse. Partial positives pointed in, negatives pointed out. And since I'm drawing this in 2 dimensions, I just drew 4 molecules around it. Turns out when things dissolve in water in 3 dimensions, usually it would be 6 molecules surrounding each one. All right. So, yep. Question. Yeah, so the question is, would the other molecules, if you went further out, now arrange themselves in a specific way? Because, you know, now it's like we have a bigger, in the case of the sodium plus ion, now it's like we have a bigger shell here with positive charges all around the outside. And yes, the molecules, you know, on the next layer out are going to be somewhat more arranged because of that. And then as you get further away, that arrangement will kind of just dissipate as it gets bigger and bigger. But later in the year, when we talk about entropy and we talk about how much order and structure there is in things, we'll see that when ions dissolve, the fact that they make the water molecules line up in a specific way does have consequences in terms of entropy. But that's for later. All right, so we can have ion-dipole interactions. What if I have a dipole? What if I have a polar molecule interacting with something that's not polar? There we can get what we call dipole-induced dipole interactions. So I want you to imagine for a moment having an atom or a molecule that's more or less spherically arranged. And because I changed the dimensions of the screen, this didn't show up as a sphere. So actually, I'm going to change this back just temporarily. All right. So imagine I have a nonpolar atom. It's got positive in the middle. It's got an electron cloud around the outside. What happens if a dipole approaches it? So on the next 2 slides, I showed a dipole approaching with a negative end coming near, and then a dipole approaching with the positive end coming near. Draw what you think that electron distribution is going to look like after the dipole approaches. And you don't have to draw in all the little E's like I did there. Just draw what you think the cloud would look like afterwards. And remember in these drawings that the arrow of a dipole. Oops. The arrow of a dipole has a plus at one end. This is the positive end. And then this is the negative end where the arrow is pointing. All right, are you ready for some Super Mr. Hamill animation? All right, ready? Here it comes. The dipole approaches. Boom! So when the negative end of the dipole approaches, what happens to the electron cloud? It gets repelled and pushes toward the other side of the molecule. Now, this molecule, which was nonpolar to begin with, has now become somewhat polar because it's got a partial positive over here and a partial negative over there. So we call this an induced dipole. No. So the question is about why would the electrons all go to one side when they repel each other? And the answer is you have this negative charge over here on the left. And so there's going to be a balance between the electrons all moving to the right to get away from that negative charge. But they're not all going to scrunch up too close to each other because they repel each other. So there is a balance there. But there is going to be somewhat of an induced dipole. And that's going to cause some attraction between the dipole and the nonpolar thing. All right, if I have the positive end approach, what are the electrons going to do? They're going to run towards it. So my positive end approaches, and the electrons all run towards it. And so now, again, I get an induced dipole that's somewhat negative on the left, somewhat positive on the right. So if we had to compare these things in terms of strength, so far, of the four kinds of interactions we've talked about, we talked about ion-ion, dipole-dipole, ion-dipole, and then dipole-induced dipole. If we had to compare the strength of those, take a moment, talk at your table. What order do you think they'd be in? Okay, 15 seconds. Lars, what was the discussion at your table? Which one did you think is strongest? Including ion-ion. All right. Ion-ion is strongest. Why? Because each thing has a fully positive and a fully negative charge, and they're right next to each other. So full positive, greater magnitude of charge, stronger attraction. So I agree, ion-ion is going to be the strongest. John, at your table, what did you guys think would be next strongest? Oh, John Doolan. Ion dipole, why? Okay, so there was some dissension, some disagreement about whether it would be ion dipole or dipole dipole. Okay, well, let's base it on this magnitude of charge argument. Which one has a greater magnitude of charge, an ion or a dipole? An ion. So based on that argument, which would be stronger? All right, so ion dipole would be next. And then for the last two, Max? All right, and I'll just abbreviate dipole induced dipole as DID. Yeah, so just based on knowing Coulomb's law, we can put these in order from strongest to weakest. So far, we haven't had to rely on any new knowledge, really. No. So the question is, how much stronger is one than the other? It's a good question, and the answer is really it depends on a case-by-case basis, because it depends how polar the molecules are, because there's varying degrees of polarity. But I will say this, ion is going to be much, much stronger. And the others, it's really going to depend case by case. All right, so now for the new knowledge. Now for, I mean, you've heard of these things before, but it turns out that there are some especially attractive polar molecules. And it comes when hydrogen is covalently bonded to nitrogen, oxygen, or fluorine. When hydrogen is bonded to one of those atoms, here, I'll just make it, I'll make it oxygen, because that's the most common. Hydrogen gets a really big partial positive, oxygen gets a really big partial negative. And that's because nitrogen, oxygen, and fluorine are the three most electronegative elements. And that big partial positive and big partial negative ends up making one molecule really attracted to the next molecule. So when you think hydrogen bonding, the first thing that should come to mind should be water. And on the next slide, I showed two water molecules. And I want to be clear. Hydrogen bonds are not covalent bonds. Do not call them bonds. Do not talk about bonds between water molecules. If you want to refer to hydrogen bonds, you must say the whole thing. So I talked earlier about how I don't want you talking about bonds between molecules. Hydrogen bonds are not bonds. They are hydrogen bonds. If I could wave a wand and change their name to super strong dipole forces involving partially positive hydrogen, then I would. It's longer, it's more cumbersome, but it would at least help us avoid using the term bond incorrectly. So when you want to talk about hydrogen bonds, say the whole thing. Say hydrogen bond. It is different from just bond. Ralph? So the question is, these elements are diatomic in their elemental state, but that really has nothing to do with it. No, that's an unrelated fact, that these elements all happen to be diatomic in their elemental state. Because chlorine is also diatomic in its elemental state, but doesn't make hydrogen bonds. All right, so I want to be clear. I've drawn two water molecules here. How many hydrogen bonds are shown on the screen so far? All right, I hear responses of 1. I hear none. I heard 4. I heard 2. So I want to be clear. What's shown on the screen? I have covalent bonds. 4 of them. 1, 2, 3, 4. Those are not hydrogen bonds. You could argue that there is a hydrogen bond shown on the screen, although there's nothing there indicating it currently. The hydrogen bond is the attraction between this oxygen over here on the right and this hydrogen here. So that dipole attraction there is a hydrogen bond. Now, hydrogen bonds are relatively strong for dipole forces, but they're still only about 5% as strong as a covalent bond. As far as intermolecular forces go, that's really strong. But compared to actual covalent bonds, it's really weak. So I want you to remember that idea that, yes, we use the term bond, but it's not in the same league. And I think I'm going to leave the explanation for why they're so strong and then the discussion of donors and acceptors for tomorrow. So we'll wrap it up there. Are there questions before we wrap up?